And I think it will be Marcello, is that right? Because I believe both Marcello and Matteo have registered from this paper. Yes, Marcello underlined. Good.
Okay. Can you hear me now?
Yes, we can see you. We can hear you, Marcello.
Great. Yeah.
Very welcome.
Hello.
And,
hello.
Floor is yours.
Okay. Thank you very much. So first, thanks the committee for this opportunity and welcome all to my talk. I first introduce this work through a realistic example. So from the medical domain to clearly frame the purpose. So this picture represents a portion of a medical ward with an emergency room surrounded by 4 corridors. A nurse moves and operates in the emergency room using the medicines that are released by the robot on the table inside the room, as you see. The stretcher bearer and the robot can only move in the corridors, as they are not allowed to traverse the room. The room has 3 entrances, as you can see, that can be either open or closed. And the nurse can open the doors to receive medicines, while the stretcher bearer sometimes might close the door to move. The goal of the developer in this case is to define a controller for the robot that prevents the robot from bumping into the stretcher bearer, but always guarantee that the delivery of the medicine within a specific time frame. So bear in mind that the duration of the agent's action is actually irrelevant. So in the case of movement, it depends on the speed of agents and the length of path they cover. Developing a controller without any automatic support is actually not easy. So the multi-annual robotic roadmap, it's an H2020 project, actually pointed out several hindrances to the development of such application. Here we have some examples. So lack of consolidated engineered processes, craftsmanship, sometimes the need for highly specialized designer, ad hoc solutions. So our target goal is then to make the development of robotic application accessible also from high-level logical perspective. So we advocate a development process that allows designer to make first a rigorous high-level design of the problem domain and of all the components of the robotic application. So at this stage, the developer should account different scenarios, environments, sectors, their actions, and define the high-level robot tasks, and possibly also verifies the application feasibility at the same time. Of course, low-level details are deferred to a later stage of the design. The controller synthesis problem, of course, has been deeply studied in the formal method domain. But however, in many cases, their immediate usage is difficult. So for this reason, our methodology takes advantage of a high-level user-friendly language with a precise and well-defined semantics, which can be integrated with off-the-shelf tools that enables the automatic controller synthesis. This would allow us to conceal the complexity of controller synthesis and allows us to make the usage of formal techniques accessible to robotic domain, to people in the robotic domain. To design our solution, of course, we consider some requirements. So first, designers should be able to model scenarios where robots and humans collaborate with each other. Robots will increasingly be used to help humans in the future, of course, in many contexts. So this is fundamental. Second, since human behavior is often unpredictable, the designer should be allowed to specify which agent in the scene is uncontrollable, as it spontaneously moves or performs events. The controller synthesis also should consider missions with specific timing constraints that are very common in practice, such as in our running example, the medicine needs to be delivered within 60 seconds, for instance, once it has been requested. Finally, the modeling activity, the analysis, and the controller synthesis cannot be done regardless of the physical layout of the environment where agents act. So the duration of the motion and the duration of action actually matters. Designing, of course, our solution requires several working assumptions. They allowed us to define a precise scope of the modeling and the analysis, and here I briefly summarize all of them. So first, it's reasonable to assume that agents are capable of doing a limited set of action. So action can be instantaneous or not, and in our model, they are always bound to a physical location, unless the action is motion. In doing their task, every controllable agent behave rigorously according to a user-defined and application-dependent plan. And also, during their operational phase, agents can collaborate with each other. So we conceive collaboration as the execution of a single action performed by two agents at the same time and on the same physical location. So one performs the collaborative action and the other reacts to that action. Also, since agent's behavior modifies the environment, like the nurse who opens the door, then the environment influences the future evolution of the agents. So indeed, in many practical situations, it's common that actions can occur only if a specific environmental condition holds. In our case, the robot, of course, releases the medicine on a table only if the door is open. Our agents operates in a two-dimensional environment, which is logically defined by locations that agents can occupy and links among the location. We are actually not interested in the physical volume of the obstacles because we are not actually implementing low-level control algorithms. So the volumes are inherently captured by the connection, by the links. And finally, our controller of the application should be omniscient. So we assume it can know all the relevant physical variables like the position of the agents, the internal timing of the robots, and the environment state. Again, finally, we assume that robots are equipped with suitable low-level control functions that control, of course, sensors and actuators. So trajectory planning, motion control, collision avoidance are not part of the outcome of our solution. So all the requirements and assumptions that I explained led us to the workflow shown in this slide, which captured our model-driven development approach. So our approach is based on a textual modeling language with a formal semantic, which is called PuRSUE-ML, that eventually, as you see, can be compiled into executable controllers. The semantics of the language is defined in terms of time game automata. The controller synthesis problem solved by Upaltiga is expressed on the TGA model obtained from a PuRSUE-ML specification. The targeted technological framework is robot operating system, which is very popular in industry and also widely supported by many educational robots. Now I will give you some ideas about the language and the TGA model. PuRSUE-ML includes construct to describe the environments where agents operate, the agent's behavior, and the goal of the application. For the sake of conciseness, I'll outline the most relevant ones. So the agent actions can be defined by using keyword events. So in this example, we are defining an action, take medicine, which can be carried out at the closet of the medicine and that lasts 2 time units. Bump into is another action, is an instantaneous action which models a collision between the medical robot and the stretcher bearer. The agent tasks can be defined by using keyword rule. In this example, we are defining a task that requires the execution of take medicine before any medicine delivery at the doors. And finally, the task terminates with action confirm delivery that indicates a successful delivery. Agents are defined by the keyword agent that allows designer to specify the set of action that agent can carry out, the set of action that agent reacts to, and if the agent is controllable or mobile. So notice here that bump into, which is the collision, is a collaborative action because it is performed by the stretcher bearer while the medical robot reacts to it. In our example, a successful mission requires that the medical robot completes the delivery of medicines that is modeled by do confirm delivery, and no collisions occur. That is modeled with the second part, stretcher bearer, never with medical bot. So never with is a keyword that captures the positional avoidance. In PuRSUE, we provide three main classes of objectives that are summarized here in this slide. So execution, reaction, and avoidance. The PuRSUE-ML specification is then translated automatically into a time game automata, where every element of the specification is rendered into an automaton. Position and state avoidance objectives are not translated directly into an automaton, as they are encoded by means of formula over locations of an automaton. And altogether, they define the reachability safety gain, modeling the robotic application that include the automata, the set goal of winning configurations, and set safe of allowed configuration. So if a winning strategy actually exists, so if the objectives are actually feasible, then UPAL-TIGA computes the controller that include for every state of the system the list of possible transition that the automata should take. And practically that is stored in a textual file in the form shown in the bottom left of the slide. To evaluate our approach, we consider these four scenarios and their variants. So in the catch the thieves, a police robot should catch the human who tries to run away from the policeman in a complex environment. Work cell models a robot and a human that collaborate with each other by carrying out coordinated actions on boxes carried by a conveyor belt. And Ecological Bot is a robotic platform which moves in the office to collect garbage that is disposed by human agents. The first evaluation is a comparison between the amount of statements we write in PuRSUE-ML to describe a robotic application and the amount of modeling elements we use to define the TGA model to model the same robotic application. The result shows that in PuRSUE-ML, we write less than 20% of the modeling elements we use to define a TGA. As usual in model-driven design, a little change in a PuRSUE-ML model usually leads to substantial modification to the TGA model. So the takeaway here is PuRSUE-ML always simplifies the design phase of the application, and in some cases, the simplification is remarkable. The purpose of the second evaluation is to show the scalability of the approach. So to this end, beside the four presented scenarios that all were solved, we consider the catch the thieves scenario with an increasing number of police robots that ranges from 2 to 10. Here, the empirical evidence showed that while the translation for PuRSUE-ML to TGA is rather immediate, in all the cases and variants, the computation of the controller is often very expensive and cause memory exhausting. Our evaluation was unfortunately limited because we only had the opportunity to use the free version of TIGA, which was available only for 32-bit architecture. The last experimental evaluation has been realized by deploying the synthesized controller for the ecological bot in a turtle bot operating in a real physical environment. So here on the right, you see the turtle bot. This slide outlines the underlying Ros Compliant Architecture we adopted to instrument the application. So in Ros, a node represents a computational entity that exchanges messages with other nodes using a publish-subscribe mechanism. So circles here are topics which store the messages published by the nodes. So the TIGA controller is automatically converted into a Python script that is executed by controller node. The runtime controller instructs the robot by sending actions to it through two topics. So PuRSUE action for generic action and move base symbol goal for movements. All the commands that are triggered by the controller are also sent to the observer node to update the current snapshot of the environment state in case agent's actions modified. So in real deployment, this is done, of course, by sensors. In our experiment, this step was simulated. So finally, changes to the environment state are notified back to the controller node to make, of course, new decisions. The bot PuRSUE user interface allows the developer allows us to realize uncontrollable events. So before showing the most enjoyable part of the talk, I briefly summarize the future work we consider. So first, we would like to extend the expressiveness of the language. We also aim at other formalism modeling games and tools to do controller synthesis. And finally, we would like to use the framework to model and solve industrial cases. So I would like to say goodbye by leaving in the background this short video, while maybe questions are welcome, showing the implementation of the ecological bot, which includes 3 agents. So the robot, the human, who throws the rubbish in the trash bin, which in this scenario is moved by an unmodeled human agent. On the right, you see the layout of the environment, and the bottom left camera indicates, the point of view where we see the scene. So this is our result. So thanks for attending the talk.
Quiet admiration.
So in this scenario, the bin can be moved. So the strategy also takes into account this.
Could I ask a question, please?
Yeah, sure.
Go for it.
Hello. Hello, Marcello. Thank you very much for the presentation. Very nice work. I'm very admiring of it, especially the fact that you go all the way to deployment and do these physical experiments. Extremely important to be able to insert yourself in the robotics community. Very nice. I had a couple of questions. The first one is, your environment seems to be based on the existence of a map, 2D map, and so on. How do you see a generalization of this technique to consider more less structured environments, let's say?
Yeah, I see the point. Actually, so our experiment were done using TurtleBot, which is equipped with the internal environment scan feature. So this actually was limited to scenarios where the environment is fully known. Well, the problem, when we move to unknown environment, could be much more complicated. I would say probably that we might even consider, maybe also probabilities in the model. where the designer can try to sketch the definition of the environment, maybe providing different probabilities in the definition of the behavior of the agents. So this might be one possible solution if we don't know actually all the map, or if we have gray areas. Well, probably we have to investigate some specific algorithms to which at runtime, which might provide an estimation of the environment.
Okay, all right. Do I have time for a second question, Olga?
A quick one.
A quick one. Okay, I've been cautious in my group of Ros because the community has reported so many bugs and so on. And so when you're interested in assurance and certification, Ros can be a bit of a problem. But yeah, collaborators from industry have come back to us and said, and what about Ros? So I wondered if you would give us some of your experience in using Ros, having done all this work, work in a very principled way to synthesize your controllers. How has been working with Ros?
So how was it, Ros, in our experience, right?
Yeah, absolutely. Did you find any flaws? Did you end up having bugs, not because of your work, but because of Ros? What's your experience?
No, as far as I know, we didn't actually find specific limitation or bugs in Ros. Yeah, so this was our experience. I remember that the main problem here was the simulation of the environment. So because we actually, so we didn't have a specific framework or specific sensors, framework of sensor to get information from the environment. So this was our main let's say obstacle, but actually we didn't find any problem with Ros as far as I remember, actually.
Okay,
thank you very much for the question.
Thank you too. So,
thank you for the questions, Anna, and thank you, Marcello, for this paper, for your presentation, and congratulations again on being selected for this. And your award is in the chat and will also be an email.